Morning, everybody. Get my glasses on. Okay, thanks as always for getting up. Morning, Cappy. Morning, Brooksy. Who else is out there? Sorry about the slurp. Morning, Vince. So I hope you're all doing good. We're gonna make it. I'll just bring up my browser, and we are getting there. So 3 weeks of class. So one thing I want you to notice though is because the college just converted the finals week to one last week, um, I can't have a weird schedule. So um, the week of May, what is today? Today's the all right. So May 26th will be a Tuesday, and we'll meet as usual. I think that's probably our last meeting, so uh, we won't need to meet on the Thursday that week. So anyway, just take note of that the last week has been converted to a normal week, but uh, what I'm hopeful of is that we're just going to finish that day and be done for the semester. So we've got, if we can just get through 7 more of these, we're all going to be good to go. Morning, Davis. Morning, Dice K. Oh, let me show you. So um, I asked my wife to get some snack bags so I could put my little electronic components in it, and I got one of these. Can you see it? So it's the super technical NASA version of the frozen Ziploc snack bag. Anyway, also says Disney on it somewhere. Can you see where it says Disney? There you go. Anyway, so that's where my electronics are going now. I'm about to pop open a new kit because I have some people who are turning in some late labs, and I need the old lab wired up. So anyway, that's why the baggie. I thought you might appreciate my frozen um, electronics component baggie. Okay, so if you've been peeking ahead, which you may or may not have been, but if you had been peeking ahead, you may have noticed that I did a little bit of shuffling in the last few homework assignments to put the content in a better place for where we're at. So last week we did the fizz buzz problem. Um, and the original homework for this week, I guess I forgot what order they were going to be in. So anyway, homeworks 13, 14, and 15. We're going to do 13 today. I think they're all 10 questions, but there has been a little bit of a shuffle, so if you've been peeking ahead, just please note. Yeah, so lab 15 actually only has 5 questions on it. Okay, so we're on homework 13, and I'm just going to go through and sort of hunt down the answers, and then when I hit something that I think is interesting, I'll talk about it a little bit more. So here we go. So you've already had your first taste of macros, and now we have some questions about it. So what I'm going to do is I'm just going to open up the links and go do some reading. So what is the purpose of the dot macro and nm? This GNU, by the way, if you don't know, GNU is, that's how you say it, by the way, GNU. What it stands for, though, it's kind of recursive. It stands for GNUs, not Unix. But probably most of you know this. GNU is a project that creates tools for programmers. So they create C++ compilers and C compilers, and they've created text editors. They even have their own operating system. So those of us who like to use free programmer tools, we use a lot of GNU tools. And in your class, the assembler and some of the other tools that we're using are GNU free software project tools. One of those tools is the assembler. So GNU AS means the assembler maintained by the GNU project. So in the GNU project's assembler, which is what we use to do assembly, what do those two things mean? Okay, so open up the macro link. These usually are in order. I bring the link over when I find an answer to the question that I like, except for I wanted to right click it. So what are .macro and .endm? And often I ask these questions, you're probably used to this as well. Many of them are just as obvious as the first thing that you read. So what do they do? .macro and .endm allow you to define macros that generate assembly output. That's it. So I'm going to copy that and paste it into my answer. That's the whole answer. That's how you create a macro in GNU assembly, which is the assembly language that we are using in our class. Technically, we're using GNU assembly for ARM processors. So they generate assembly output, and I'll describe this more when we get to doing the lab, but they look like functions and they feel like functions, but they're not fully functions. What they actually do is every time you call a macro, it generates a full copy of the contents of the macro in the place where you called it. That's a little bit different from a function, because in a function, the flow of execution actually jumps into the function, executes it, and then jumps back to where it left off. But in a macro, all it does is at assembly time, it goes and grabs a copy of that code and pastes it at the point where you called it. So that's just, we'll look at that more closely on Thursday when we do the lab. All right, so now it asks us to write some. So define a macro named add1. So the whole point, though, is that macros are places where you can sort of create reusable chunks of assembly, which feels like a function. If we look at the page, by the way, just clicking back over to chat. Anyway, if we look at the macro page, the example is elaborate looking. It's not as simple as we can get away with. So I'm going to scroll down a little bit. Okay, I don't see any examples here that I like for something this simple, but fortunately I know what to do, and I'm going to show you. So macro and .endm are how you. Can I bump this up one? No, not pretty. This is how you create a a block of assembly code. And then next to the .macro, you put what you want to call it. So we want to call this one add1. So add1 will be the way that we refer to this macro when we need a copy of this code introduced into our program, which we're not writing a full program, but that's how it would work. You can't tab in here, by the way, so 1, 2, 3, 4, just to get over. The body of the macro is simply to add to R0, 1. That's it. That's the whole add1. This isn't a particularly useful macro, but the point is, when you create a macro with .macro, .endm, you give it a name, and then you do the assembly code that you want to associate with it. I could have said, by the way, I did the R0 plus equals 1. I could have done this, and I could have put the pound sign for the literal, but the GNU assembler is more than happy to just take this as a R0 plus equals 1. Okay. So this one wants us to write another one. So write another macro. So .macro, .endm, and then call it reset counter. And I'm going to put a little bit of space. This language is not white space. You can use white space all you want, so you can kind of spread things out if you think that is easier to read. Reset counter. So what does it do? Tests the value in R1 and sets it to 1 if its current value is 0. So what we're really doing is a equivalence. And there's a couple of ways to do this. I like the test equal because I like setting the if then blocks up. 1, 2, 3, 4, 5, 6, 7, 8. I'm just going to push that out. So what I want to know is R1 equal to 100? So the point here is you can put an if then block inside a macro. You can put any assembly code. If then it proves to be equal to 100, then I will move on it being equal to 100, 1 back into R1. So the question number 3 really just sort of asks you, okay, we do something super, super tiny and we do something slightly bigger just to ease you into the idea and get you comfortable with it. So that's it. Dot macro, dot endem, we give the macro a name and then we place in between those two dot macro and endem the assembly code we want to associate with that name, reset counter. Okay. Can you pass arguments to GNU AS macros, and can they have default values? So I'm going to go back to the macros page. Probably, since we're all programmers, we have the sense that this macro named sum, that's probably an argument list. So probably the answer is yes. And if you've done some C++, then you might recognize this kind of looks like default arguments. But let's look. I'm going to use Control F, and I'm just going to look for the keyword arguments in here. So if your macro definition requires arguments, specify their names after the macro name. So the answer to whether or not they take arguments is yes. Yes, you can pass arguments to GNU AS macros. Can they have default values? That's what this looks like to me in the example up here, but why don't I use Control F again and just see if that keyword default is in here. You can supply default value for any macro argument by following its name with an equals. So that's what this is showing up here. The macro called sum takes 2 arguments, a from argument and a to argument, and the from argument has a default of 0, the to argument has a default of 5. That means those are optional, if you remember default arguments. I'm not going to worry about this long. Who cares? That's a mess. But that answers my question. So, yes, the arguments can have default values. Those are just things, information gathering about GNU assembler macros. Hopefully I've not moved that stuff off the screen too quickly. That's all the macros part, so I'm going to leave it there for a second, and if you need me to hit pause, you can let me know. Oh, Kevin, sorry, I forgot to say good morning, Kevin. I didn't see your hello come by. Sorry about that, man. Anybody else who's come in, good morning to you as well. In our assembly class, we've gotten a tradition among the regulars that we do a greeting, which feels good, because this is a lonely business. Okay, so on we go then. Let's hit. So number 5, the include directive. So there's another link for that, so let's go read that. And I think this is one is like gloriously short. Okay, so the question is, number 5, what is the purpose of the include directive? You kind of have a sense of that, but this is a little bit different than a C++ include, possibly. So let's go read so here's include. Oops. The way you use it is to include some file. So this directive provides a way to include supporting files at specified points in your source program. Now, the code from file is assembled as if it followed the point in the include. What that means is that you can use an include in GNU assembly, and it more or less literally pastes in that stuff at the moment that you have the include. So an include can be anywhere, and it can have anything in it in a GNU assembly, as long as when you do an include for a file, the contents of the file make sense in the flow of your program. Now for our includes, we just tend to put them at the top because that works, but that's just something to note. So let's see, I'm going to take this. So this, I like all of that. So this directive provides a way to include supporting files at specified points. The code from file is assembled as if it followed the point of the include, meaning it sort of just takes the contents of the file and pastes them in right at the spot where you do the include. And when it hits the end of the contents of the included file, then the rest of the program just keeps going. So that's pretty good. I don't care about controlling search paths. That's something else. So I'm going to take all the way up to assembly of the original file continues. I'm gonna, yeah, that's adequate. And what's the, yeah, this directive, that's pretty good. Just gonna leave it like that. And again, that question's there because we used an include last week, and we're gonna have them for the rest of the lab. So might as well go hunt down what really is going on with the include. Okay, that's the only one for that particular document. So now we're on number 6, which asks about arrays. So let's go grab the reading on arrays and structures. Some of this stuff is hard for me to find sort of readable documentation. So what you'll see me do sometimes is it seems like it's coming from the wrong place, but sometimes I find them in this Raspberry Pi online content. You probably knew this, but if you didn't, Raspberry Pis run on ARM processors. So their underlying processor functionality is the same as what we're exploring here. Okay, so anyway, that's why I can use this content in here. So let's see what the question says again. How many bytes are needed for an array of 25 integers? So this is going to take some reading. I'm assuming that you know what an array is, but if you don't remember, this page actually defines it. So an array is a sequence of items of the same kind in memory. More important than that, by the way, it's a sequence of items of the same kind in memory that are all that are sequential. They're all next to each other. So the entire array's memory is side by side by side, which is important because that's how we do things like indexing and get fast access to array elements. Okay, so now we're just going to keep going. So defining arrays and structs. What I'm looking for is something that tells me about bytes. This looks pretty good. So let's define an array in assembly. So here's an example in the C language, and then he says let's go do it in assembly. So for 100 integers, an integer in ARM is 32 bits. We know that because we've answered lots of questions about that. 32 bits, which is 4 bytes. That's 8 bits per byte. So 4 bytes makes 32 bits. So 4 bytes. So to do 100 integers, we need 4 bytes per integer times 100 integers is 400 bytes. So there's our clue. So for us, we have 25 integers times 4 bytes per integer. So remember, a byte is 8 bits. So how many 8-bit things go in 32 bits? There's 4 of them. 4 bytes per integer. Which gives us 100 bytes. So it's asking me in bytes how many bytes are needed, so 100 bytes. And then it's asked me to write the code to actually do that, and I'm going to go back to the document. So this is kind of weird because you have to do the mental gymnastics of bits, bytes, bits and bytes and bits and bytes. You just sort of have to stop and think for a second. All right, in ARM, integers are always 32 bits. So how many bytes is that? That's 4 bytes. So if I need 25 of something that requires 4 bytes each, that's 100 bytes. Why bytes? Well, for now, why bytes is because it asked me to do bytes. That's why. But it turns out that when you're calculating storage space in assembly, you do it in terms of bytes, not bits. So to calculate storage space for an array of 25 integers, we need to know how many bytes that would be. Okay, the second question is write the ARM assembly code to declare an array named numbers of 25 integers. So let's go back and see how he did it, because he did it here. I'm not going to write the data part. Oh, what the heck. Let's just grab it. Let's grab all of it. That's what this document says we do. Technically, this is for us is section data. But why not? It doesn't hurt anybody. So the assembly code, we'll talk about this B-align. This means byte align. So if you look at his documentation, he named his array A. So we want the array name numbers. And then he needed 400 bytes. And we need 100 bytes. I'm going to smush these up just to... This is a good reminder that if I were to declare an array, I would do it in the data section of code. We're going to do this on Thursday, so I'll refer back to this. So hopefully everyone saw how I brought all those pieces together from that document. Okay, so because we used the keyword, the directive skip, I went ahead and asked a question about what does that skip actually do. So number 7, let's go, I think I linked a document, I did. So let's open up skip. Skip, this is easy. So the skip directive emits size bytes, each of value fill. Both size and fill are absolute expressions. I'm not even going to worry about that. I'm going to leave it, but whatever that means. If the comma and fill are omitted, which means that you can omit the comma and the fill, then the fill is assumed to be zeros, which is the same as dot space, whatever that means, but let's just take that. So the skip directive allows you to omit a certain number of bytes. That's what it does. In assembly, if you use the skip directive, it emits a certain number of bytes. I'm actually going to put the signature here because my answer doesn't make any sense. What is size and fill? So I think my answer makes more sense if I put the signature in there. So if I use the skip directive with the size, it emits that number of bytes. So if I look back at this one, number 6, the skip directive is being used to emit 100 bytes. Why 100 bytes? Because that would be the amount of space I need to get myself storage for 25 integers. So numbers effectively is an array of 25 ARM integers. 100 bytes worth of memory, back to back to back. Notice, by the way, I don't have the comma or the fill, because it tells me that those are optional, and if I leave them off, I get zeros. So what I get here is 25 integers whose initial value is 0. That's what it's telling me down here. If the comma and the fill are omitted, the fill is assumed to be 0, defaults to 0. Hopefully that makes sense. That's meaningless to me right now, but probably that means that I could fill with the 0, or I could do a dot space, and maybe that means fill with zeros. I don't know. But if it's already going to fill with zeros, let's just do that. Seems sensible. And then again, especially for the video watchers later, just sort of pay attention to where I'm doing some. This this text in number 7 makes a lot less sense unless you have the signature of the skip directive that then explains what size and fill are referring to. Okay. Write the ARM assembly instructions to do a lot of scary stuff. But some of it's not that scary because we've done it before. It's a long time ago, um, but we've done this before. So write ARM assembly to 1, load the address of numbers using the equals. It's telling me that I'm assuming that I'm talking about my array, but whatever. Let's just get the address loaded up. 1, 2, 3, 4, 5, 6, 7, 8 into where? R0. The address of numbers. So you haven't seen this setup before, but what this effectively does is loads up the address of the start of my 100 bytes into R0. So another way of saying this is that R0 is the address of my array. It's where my array begins. So number 8 is really telling me how do I actually use an array. So the first thing you do to use an array is you load up the address of the array in question into some register. The equals in this context will mean the address of. 2. Load the immediate value 1 into R1, but since it's a tiny value, I will use a move. So by load in this case, I'm going to use a move. So now R1 has the value 1 in it. What it wants me to do is put a 1 in the first slot in the array. Then store the value 1 as the first element of the array. So store that R1. The reason why I had to do the middleman is because you can't do a store with immediate values. You have to use registers. So if I want to store 1 somewhere, I first have to move it into a register. Now I can store that 1 in numbers. And because R0, dereferenced by the way, because R0 is basically the address of the start of the array, that's taking R1, which is 32 bits, and overwriting the first 32 bits of that array, which would be the first element, the 0 element. Kind of cool. And then we'll look at some alternatives that might make this seem a little bit more familiar to you. That's that whole thing. So number 8 is there to introduce you to what does it look like in assembly to access an array. You declare an array, which we did in number 6. You get the address of the array. You put some data in a register, and then you can take that data and write it into the array. So the value in R1, which right now is 1, is written into the array R0. And what that really means is these 32 bits that are R1 are written 32 bits wherever that R0 is sitting right now, which is at the start of numbers array. If you remember zero-based indexing, that's kind of what this looks like in assembly. So that's numbers at 0. In C++ or C, we'd say numbers or go equals 1. So that's what that did. This 0, by the way, means don't move in. Just the first 32 bits. So that's all that code does. Takes some getting used to, but it's really not that bad. Okay, so now let's get some scary definitions going and then look at examples of what they look like. Non-updating indexing modes. And then I'll try to explain what this means. But first, let's go get ourselves a definition. So I'm going to go back to, I need my array page. Is this my array page? Yeah. So I need my array page again. And then I'm going to scroll down until I see non-updating indexing mode. So this must be where that question came from. So, I mean, I'm just saying all this is words, but this relies on the idea that you understand indexing. So, in high-level languages, we do indexing all the time, right? I did one here. This is what it would look like in a high-level language. So that's what we're talking about is how do you access a specific element of an array with an index. And it turns out that in assembly there's actually two ways, sort of two major ways to access an element of an array. One is called updating indexing and the other is called non-updating indexing. And we're about to look at some examples. So all we're talking about here is if I have an array, how do I get an element from that array? Well, I use an index. In high-level languages, there's only one indexing mode, but in true assembly, there's, in this case at least, there are two indexing modes. Okay, so I don't like the way this is worded, but that's basically what it is. Non-updating indexing mode just adds or subtracts an immediate value to form an address. So let's get the answer, which is that. I'm going to make this read nicer. So I'm going to say non-updating indexing mode adds or subtracts the immediate value to form an address. That sounds a lot worse than it is. So let's look at an example using numbers again. So we're going to 5, 6, 7, 8. I'm just spacing over so it's a little more readable. Let's do the same process. Where we get the address of our array, we're still going to refer to the numbers array from question number 6 or wherever that was. I'm going to get it. And then let's populate it a little bit just for fun. So this will be examples of non-updating indexing mode. Let's do a couple of examples. And I know that I'm going to switch back over to the page. If you look at this, this is what it looks like. And what this is saying, if you look at the text above, so if we want to write the value 3 into an array, we first move the 3 into a register, and then we do a store with the register containing that value. So this argument here is where the array starts and how many bytes to offset into it. I'm not sure if we'll try it without the pound sign. Anyway, how many bytes to offset into it? So we'll just think about that for a second, and I'll show you an example. So let's say we want to populate our array with 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Except for it's an array of 20. So we don't have to do that many. Let's just do like the first 5. Dot, dot, dot. Okay, so we want numbers at 0 to be 10, numbers at 1 to be 20, numbers at 2 to be 30, numbers at 3 to be 40, and numbers at 4 to be 50, and then we'll just ignore the remaining 20 integers. Okay, so what does that look like with non-updating indexing mode? So we're going to move, use R1, and we'll put the value 10. That's our first value to go in. Then we do a store of that value. And then here's non-updating indexing mode. So this is the array. Is it R0? Hold on, I got a cough. Actually, just clear my throat. Okay, that's better. Okay, so non-updating indexing mode means that we say, starting at some array base, this is where the array starts, how far to offset. For the first element, we'll offset 0 bytes. We just want to affect the first element. This is non-updating indexing mode, and what that means is my R0 doesn't change. I still have R0 being the start of the array, and then I supply an offset to say how far off of the beginning of the array do I want to move. If I move 0 amount, I'm at the first element, which is where zero-based indexing comes from, by the way. 10. So we'll do a couple more non-updating indexing modes. So for the second value, I can't get these to line up because it's not a fixed width font, I guess. We're going to do 20, and then we're going to store. Now R1, we just put 20 in it. Going to go to our same array. That's where it starts, and then we have to figure out how many bytes to offset. To get to the first one. Now in a high-level language, we just say 1 over. But in assembly, how many bytes do we have to move over to get to the second one? And I'm going to wait this out and see if anyone in chat can come up with the answer. 4, outstanding. 4 bytes. 4 bytes over. So one thing that you'll notice here is when you're programming in a high-level language like C++ or Go or Java or whatever, you don't have to think in terms of how many bytes do I have to offset to get to my element in my array. The language actually does that calculation for you. But in pure assembly, you actually have to say, I need to move over that many bytes. So we're going to practice a few more just to make sure I get the point across. So the third one would be 30, and then I'll store it. Oops, that's supposed to be R1. That's my middleman. So R1 into, go back to the same. So when we say non-updating, what we mean is R0 never changes. R0 is always the base or starting point of the array, and then we use an offset. But the starting point, R0, never changes. The only thing that does change is our offset. So same thing here. How many bytes do we need to move or offset to get to the second integer? Man, I'm out of T. Gone quiet. See if anyone comes up with this one. So how many bytes is it from the beginning into the, well, now what's now the third element, right? The third element. Oh, wait too long. I don't want to waste your time on sort of just dead air. 8! Outstanding. Yes, it's 8. So 4 bytes per. So if we were to write in a high level language, these numbers represent, right, increments of 4. So in C++, we'd say numbers at 2, but what we really mean is numbers 8 bytes over. So it's perfect. And then I'll just sort of hammer through the last couple really quickly. So this element, if I were to store it into the array, and again by non-updating indexing mode, what we mean is the R0 part, the base address, the starting point of the array, never updates. That's always, it never changes. So the moving target is the offset, not the array address itself. That would be 12. And then the last one, that's getting pretty long. Stretch it out some. Will it stretch any? Yeah, it will. All right, so hopefully you get the point. This is, it seems that when you first see that documentation, like, I can't make any sense out of that stuff, but it's actually not that bad. The point here is that in assembly, when you're dealing with arrays, you need to think in terms of how many bytes do I need to move. One thing that they said, by the way, which I'm not going to do, but you can do something like this. So I'm just going to put junk in here just so you don't. So I don't find myself doing this that much, but what they're saying is you can actually make this number be negative. You put that in between. You can make this number be negative, and that will move back. Now that's potentially a terrible thing to do, but you can actually use negative offsets and go backwards in an array. You just have to be careful that if you're going backwards, you need to be going backwards from somewhere that it matters. So you might, for example, I don't know why you would do this, but you might make this address be the end of the array as opposed to the beginning, and then you could offset backwards. But we don't really need that. Hopefully everyone gets the point about non-updating indexing mode, that it's a way to access the elements of an array. Given an array address, you specify a number of bytes to offset into it, which is how you access individual elements of it. And we call it non-updating because the base, the starting address, R0, never changes. It's always the same place. That's what we mean by non-updating. Okay, so now let's go back to this. So now we'll do number 10. Updating modes. So if we scroll down, there is an updating indexing modes. And in these modes, okay, so I'm going to grab this. In these, a register is updated with an address synthesized by load or store instruction. That sounds pretty scary, so we'll do examples of that as well. But in updating, just improving the quality of that answer. In updating indexing mode, I don't like that word. I'm going to change that. So in updating indexing mode, I'm going to say a register is updated with the address synthesized by the load or store instruction. Now that just sounds awful, but it's not that awful. all that really means is, and we'll do some examples, non-updating means the R0 doesn't change, and in updating, the R0 actually changes. So let's look at how that would work. So examples of updating indexing mode. We're going to do the same stuff. We're going to load 4, 5, 6, 7, 8, get the address of our array. Let's just do that. We want to populate our array with, what the hell, I'm just going to change the numbers because I don't know why. 3, 6, 9, 12, 15. We'll just hit the first 5 just to make us think a little bit. So this is a different way of accessing the array, is with updating indexing mode. And what you're going to see me do is move the base of the address over. Okay, so the first one, 2, 3, 4, 5, 6, 7, 8, we'll put the value 3 in R1. And then we will store R1 into R0. Now this looks familiar because we've done it this way before. But when you're doing updating indexing mode, typically you're not going to use offsets. R0 is sitting on the location where the next 32 bytes needs to go. So that's it. That's numbers at 0 equals 3. All right, now it gets more interesting because in updating indexing mode, I'm not going to write a note about that. In updating indexing mode, what we do, I'm just going to do it easier. I don't know if this is a good way to say this, so we might sort of change the way we're describing it. But in updating indexing mode, instead of using offsets, I literally just move the marker for the array over. Now they did it in a super fancy way, but you don't have to do it in a super fancy way. All I'm doing here is I'm just going to add 4 bytes to R0. Now what does that really do? Well, it sort of appears now that the array begins 4 bytes over. It's not true because I'm not losing the original value 3 that I placed at the beginning of my array. All I really did is move the base address, or the marker where the array starts, over 4 bytes. That doesn't move the array itself, it just moves where my code thinks it starts. So I have updating indexing, I have updated the base address to be 4 bytes over. Six. And then I'm going to go quiet and I'll wait for an answer. What goes here? Outstanding. Yes, that's exactly right. R0. And the reason is because I updated the marker that shows where I'm at in the array right now. So in updating mode, I'm using a marker on the specific element I want, and I move the marker around. In non-updating mode, the marker stays the same, and then I have an offset that moves around. In updating mode, the marker actually moves around, if that makes some kind of sense. So I'll go a little bit faster through the last couple. Um, so that's really, if I keep track of what I'm doing, I know that I'm one integer over now. So to get to the next one, I'm going to add, so I'm going to move over yet another byte. And I'll go ahead and finish the thought, but I think, um, I hope. I'll do one where let's see, that is numbers 2 equals 9. All right, so I'm going to do one with a mistake. Let's just see if we can unravel my mistake. Um, all right, so this one you kind of have to study for a second and see if you can figure out what's the mistake. As we come up here to the end. Yeah, in fact, so Brooksy asks, is the marker kind of like a pointer? It's precisely a pointer, in fact. So since pointers are just addresses to a place in memory, that's really what the marker is. I mean, truly what it is. It's just an address to a spot in memory that we're moving around. So yeah, that's exactly what it is. Good point. Oh, Vince caught it. So good one. So good question, Brooksy. Hopefully that answered it. And Vince caught the mistake. Um, the mistake is that numbers at 4 now equals 12 instead of numbers at 3. Um, so the last question I'll answer is then where was that? Where did that happen? So where did it happen that I skipped over numbers at 3, at index 3? Nice. Outstanding. All right, so I'm feeling really good because I think everyone sort of gets that here. So right here, so hopefully everyone gets this. The updating indexing mode is literally is where you move the marker around, and non-updating is where the marker stays the same, and then you have indexes to move around to get to what you want to. Um, so you guys are on top of it this morning, which is really good because at least for me it's still kind of early. Okay, so when you are programming an assembly, you can use either of these styles. Um, it doesn't matter, they both work to achieve the same result. It's usually a matter of what you feel more comfortable with and perhaps what is simpler to pull off in code. So on Thursday, we will be doing some of this indexing, um, and we'll just sort of decide as we work through it if we want to use updating indexing or non-updating indexing. I'll probably try to make us practice with both just to see what that feels like. Um, so that was lots of examples there. Hopefully that made sense. Okay, we're good on chat. Let me bring up. I don't want to lose that stuff. I'm pretty happy with that stuff. So let me bring up a separate one and just to prepare for Thursday. So we have 3 labs left. There's lab 14 this week, lab 15 next week, and then the last week we call the final lab, which if we have to, we'll finish that during the week of May 26th. But anyway, we have 3 labs left. Lab 14, and this is just to bring up the diagram and show you. This is going back to an earlier lab that was a little bit simpler. So basically that three-legged LED gets removed. Um, I don't remember. You might look and see lab 15 and the final lab if it comes back. But anyway, I'm going to have this circuit for Thursday, and then as part of the warm-up part of the class, I'm already going to have the breadboard built, and then I'll do these final connections to my Nucleo board as the warm-up part of the class. So on Thursday, we're doing lab 14. We're going to put an array in there, and then we're going to have a display that cycles through the values of the array and displays the values of the array as opposed to just running a counter and displaying it. So that's what's going on Thursday. Okay, so that's everything I got for today. I'll sit here for a couple minutes and see if I can answer questions. So if you can, your life will be easier probably if you have the circuit ready to go. And then we can just, after my little warm-up bit, get right into the code for the lab. Okay, I'll bring that back. Thank you, appreciate it, Brooksy. Hopefully I'll see. Um, yeah, Davis, you get to spend a lot of time with me on Tuesdays and Thursdays. Sorry about that. Um, you too, Brooksy. Thanks. Have a good one. Have a good one, everybody. I'm here at 10 in the morning if you need anything. Probably for this class. Most of you don't. Yep, Thursday. See ya. Everyone have a good today and a good tomorrow, and then we'll be back on Thursday at 8:30, and we're getting pretty close to the end. Okay, signing off.